Welcome, sleepy thinkers, curious night owls, and anyone drifting gently toward dreams. You've arrived at the Sleepy Scientist, where the stars are big, the questions are bigger, and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight we're going to tiptoe into one of the most mysterious questions ever asked. Did nothing ever exist? But don't worry, we'll take it slow, with soft voices and a calming curiosity. After all, this isn't a race through equations, it's more like floating through a galaxy of ideas with a cup of chamomile tea. Now, I do hope the video isn't too interesting. That would be terribly inconvenient at bedtime. But if it happens to keep your mind gently glowing, well, at least you'll be learning something fascinating while you drift. Before we begin our cosmic wandering, I'd love it if you tapped the like button, and if you enjoy gentle science journeys like this, feel free to subscribe. It helps more curious souls find their way here. Let me know in the comments where in the world you're watching from, and what time it is for you right now. Is it just past midnight, or the early glow of 4 AM? I always love reading those sleepy check-ins. And finally, while we're going to explore some deep and dreamy questions tonight, please remember this is not medical advice, just a soft place to land at the end of your day. Let's begin. Let's take a deep breath. Not to fill your lungs with cosmic insight just yet, but because we're about to dive into a subject that seems simple at first, but quickly becomes slipperier than a bar of soap in a black hole. Tonight's question is, what do we really mean by nothing? You'd think that of all the things in the universe, in or outside of it, nothing would be the easiest to explain. After all, it's, well, nothing. No things, no stuff, just emptiness, right? But here's where it gets interesting. The more carefully we examine nothing, the more it starts to look suspiciously like something. And as we'll see, in both science and philosophy, nothing can wear quite a few disguises. In fact, there are several kinds of nothing, each one stranger and more counterintuitive than the last. Let's start small, with something familiar. Picture an empty jar sitting on your kitchen counter. You screw off the lid and look inside. It appears empty. There's no peanut butter, no sugar cubes, not even a lone grain of rice. Most people would call that nothing, but of course that's not quite right. The jar is full of air, oxygen, nitrogen, a bit of carbon dioxide, maybe the lingering scent of cinnamon from whatever it held last week. Molecules are bouncing around in there like invisible popcorn. If you were an ant with a chemistry degree, you'd be overwhelmed by just how not nothing it really is. Okay, let's step it up a notch. What if we suck all the air out of the jar, vacuum seal it until there's no atmosphere left inside at all? Now we've got a vacuum, or what we might call empty space. Is that nothing? Well, we're getting closer. But even this vacuum isn't truly empty. First, there are still fields inside. Not cornfields, but the invisible kind that exist everywhere in the universe. These are quantum fields, and according to modern physics, they can never be completely turned off. Even in their lowest energy state, they still ripple with possibility. And this is where things start to get quantum weird. In the early 20th century, scientists like Max Planck and Werner Heisenberg discovered that the tiniest levels of nature are never truly still. Even a perfect vacuum, devoid of matter and energy, is still humming with uncertainty. Tiny particles pop into and out of existence constantly. They're called virtual particles, and they're part of what physicists call quantum fluctuations. In other words, even nothing is always doing something. Imagine your empty jar again. If we could make it truly vacuum sealed, removing every molecule of air, and then shrank ourselves down to the quantum scale, we'd still see things happening. Not because matter is leaking in, but because the fabric of the universe itself is restless. It fizzes with energy. The vacuum is like a quiet ocean that looks calm from above, but teems with life below the surface. So here we are, two versions of nothing down, and neither one is truly empty. Let's take it further. What if we removed space itself? Not just the stuff in space, but space itself. Gone. No dimensions, no up or down, no left, no right. Can we even imagine that? This is where language starts to fail us. Without space, we can't describe where anything is, or even where nothing could be. It's not a black void. It's not a white screen. It's not darkness, silence, or emptiness. It's the absence of place itself. You can't put your mind inside it because there's no inside. Then let's get even more radical. What if we took away time as well? No seconds ticking by, no change, no motion. A timeless, spaceless, matterless what? Some physicists and philosophers propose that this is the only true form of nothing, the absolute absence of everything, including the dimensions in which things can exist or happen. But now we're dealing with something almost paradoxical. If there's no space or time, can we even say it exists? And if it doesn't exist, then what is it? It's a bit like trying to draw a square circle. The words make sense individually, but together they become nonsense. In the same way, our brains, which evolved to track fruit, faces and predator footprints, aren't naturally equipped to visualize the absence of all things. Nothing, in its most extreme definition, might be not just beyond our senses, but beyond thought itself. Of course, some philosophers have argued that nothing doesn't make sense at all, that it's a concept invented by language. When we say something is not there, like when your friend says there's nothing in the fridge, we still mean something. We mean the fridge is present, just empty of the items we want. But when we talk about absolute nothingness, we're using words that point to an absence we've never encountered. Heidegger, the famously cryptic German philosopher, once asked, "Why is there something rather than nothing?" It's one of those questions that sounds obvious at first, but grows more unsettling the longer you think about it. And the more we learn from science, the more it seems that nothing might not just be hard to find. It might not exist at all. Even the term before the Big Bang may already be a kind of error. If time began with the universe, then asking what came before is like asking what's north of the North Pole. The question seems to make sense but collapses under its own logic. Still, it's a very human question. We crave origin stories. We like to trace things back, family trees, historical timelines, the last slice of cake. But when it comes to the universe, we may hit a wall. A soft, baffling, quantum fluctuating wall. So where does that leave us? It leaves us with several kinds of nothing, all of which are actually quite something. From airless jars to seething quantum vacuums to theoretical voids outside of space and time, nothing is not one neat concept. It's a spectrum of increasingly abstract possibilities. And in the end, we might have to accept that pure total nothingness may not be part of reality at all, only part of our imagination. But that doesn't mean the question is pointless. Quite the opposite. Asking what nothing is helps us understand what something really means. It's in the contrast that clarity emerges, or at least a kind of peaceful confusion. And as we'll see when we explore the origin of the universe, nothing may be not the end of the line, but the beginning of a very strange road. So let's keep floating gently through the questions. There's a lot of nothing left to uncover. Let's take a gentle step forward, or maybe backward, depending on how you think about time. We're going to take a calm stroll through the history of, well, everything. But don't worry, you won't need a time machine or a seatbelt. Just a quiet mind, a comfortable pillow, and perhaps a sense of cosmic wonder. Tonight, we're visiting the moment the universe began, or at least the moment our current understanding says it did. This is the story of the Big Bang. Not a loud explosion in space despite the dramatic name, but a gentle unravelling of space itself. A moment so strange that it gave birth to not only everything we see, but the very space and time in which we see it. Let's imagine you're standing in the deepest corner of space, far from any stars or galaxies. There's no sound, no breeze, just the soft hum of distant starlight and the feeling of cosmic stillness. That stillness, though, hides a secret. Because everything, all the planets, stars, galaxies, and even the emptiness between them, is moving apart. Slowly, gently, and inevitably, space itself is stretching. This idea, that the universe is expanding was one of the great revelations of the 20th century. For a long time, scientists assumed the cosmos was static, fixed, eternal, unchanging. But then, in the 1920s, a Belgian priest and physicist named Georges Lemaître had a very curious idea. What if the universe was not static, but expanding outward from a single dense point? Around the same time, American astronomer Edwin Hubble was peering through his telescope and making an equally curious observation. The light from distant galaxies wasn't just dim, it was redder than expected. Not because they were embarrassed, but because they were moving away from us. This shift in wavelength, known as redshift, was a cosmic clue. It meant space was stretching, and everything in it was being carried along like raisins in a rising loaf of bread. And if everything was moving apart, then it must have once been much closer together. Imagine rewinding the universe like a film played in reverse. Galaxies rushing toward each other, stars condensing, matter folding inward, all collapsing into a tighter and tighter ball. Until, about 13.8 billion years ago, you reach a moment of unimaginable density and temperature. A kind of cosmic seed. A singularity, as it's sometimes called. Not a thing inside space, but the point at which space itself began. This is what we call the Big Bang. It wasn't an explosion in space. There was no pre-existing vacuum, no cosmic firework lighting up a black sky. Instead, it was the sudden, dramatic expansion of space itself, the birth of time, energy, and the laws of physics as we know them. And no matter where you stand in the universe, it looks like everything is expanding away from you. Not because you're special, but because space itself is growing in all directions. It's a bit like dots drawn on the surface of a balloon. As the balloon inflates, each dot moves away from the others, not because they're travelling across the surface, but because the surface itself is expanding. That's our universe, a balloon of space-time slowly inflating for billions of years. Now, what actually happened in the first moments of this expansion? That's where things get delightfully complex. In the tiniest fractions of a second after the Big Bang, and we're talking trillionths of a second, the universe was a hot, dense plasma of particles and energy. Temperatures were so high that matter couldn't exist in the forms we recognize. Protons and neutrons hadn't formed yet. Even atoms were still a future luxury. Everything was a glowing soup of fundamental ingredients. But as the universe expanded, it also cooled. That cooling allowed energy to condense into particles. Quarks began to combine into protons and neutrons. After a few minutes, these joined to form the first simple nuclei, mostly hydrogen and a little helium. Fast forward a few 100,000 years, a blink by cosmic standards, and the universe had cooled enough for electrons to settle into orbits around nuclei. For the first time, neutral atoms formed. And something beautiful happened. Light, which had been bouncing off free particles like a strobe in a foggy room, could finally travel freely. This moment, when the universe became transparent, left behind a whisper, a kind of soft, ancient glow still visible today. It's called the cosmic microwave background, or CMB for short, and it's one of the strongest pieces of evidence we have for the Big Bang. The CMB is everywhere. It fills the universe with a faint, nearly uniform microwave signal. It's not strong. You'd need a very sensitive antenna to detect it, but it's there, like a baby picture of the cosmos, frozen in time. Tiny temperature fluctuations in this ancient light give us clues about the earlier structures, the seeds of galaxies, stars, and planets. Discovered in the 1960s almost by accident by two radio astronomers, Arno Penzias and Robert Wilson, the CMB was a game changer. They thought the static they were hearing was from pigeon droppings on their antenna. It turned out to be the echo of creation. But even with all this evidence, the redshift of galaxies, the cosmic microwave background, the proportions of light elements, the Big Bang model doesn't answer everything. In fact, it raises some tantalizing questions. For instance, what exactly caused the Big Bang? What triggered that initial expansion? Why did the universe begin in such a low entropy, highly ordered state? A state seemingly fine-tuned for complexity and life? And of course, the big one. What came before the Big Bang? That's the question that brings us full circle, because if the Big Bang was the beginning of time and space, then before might not even exist. There may not have been a before to speak of, only an origin point from which everything else flowed. Still, not everyone is satisfied with that answer. Some physicists propose models in which the Big Bang was not the beginning, but a transition, a bounce, a cycle, or the birth of one universe among many in a vast multiverse. We'll explore all of those possibilities in the chapters ahead. But for now, we sit gently with the Big Bang, not as a noisy explosion, but as the quiet, powerful unfolding of everything. A beginning not in fire but in form, not in a bang but in a breath, the breath of space itself. If you've ever found yourself staring up at the stars and wondering where it all began, you're not alone. Humans have been asking that question since long before telescopes, spaceships, or glow-in-the-dark ceiling stickers. It's a deeply natural instinct to seek origins, to trace back the thread of time as far as it will go. And when we follow that thread all the way to the edge, we arrive at a curious place. A place where time itself may have had a birthday. Now, let's pause here and let that idea settle gently. The beginning of time, not just the beginning of the universe, or of stars or atoms or coffee, but of time itself. It's a bit like finding out that your watch didn't just stop working, but actually ceased to have any reason to exist before a certain moment. To explain what this really means, we need to go back to the Big Bang, or more precisely, the Big Beginning. In the standard model of cosmology, space and time are not separate entities. They're part of the same stretchy dynamic fabric called space-time. Think of it as a vast, invisible trampoline, and everything in the universe, from dust particles to galaxies, sits and moves atop its surface. According to Einstein's general theory of relativity, this fabric can warp, bend, and stretch in response to mass and energy. That's what we experience as gravity. But here's the truly bizarre part. That same fabric also has a beginning, and that beginning, as far as we can tell, is the Big Bang. This means that space didn't explode into some pre-existing void. Rather, space itself was created in that moment. And because time is part of the same fabric, it too came into being. There was no ticking clock before the bang, no empty hallway waiting to be filled, no before, because there was no time in which a before could exist. It's an idea that defies our usual instincts. In our everyday lives, everything has a before. Before breakfast, there was sleep. Before sleep, there was brushing your teeth. Before that, probably some late-night snack you're not proud of. We are deeply conditioned to think in terms of linear cause and effect. So when someone says time had a beginning, it's tempting to say yes, but what was before that? And that's where the gently absurd analogy comes in. Asking what happened before time began is like asking what's north of the North Pole. The North Pole is the top of the world. It's not just a very cold place with polar bears and the occasional elf workshop. It's the furthest north you can go. Try walking north from there, and you'll just start heading south. In the same way, time reaches a kind of boundary at the Big Bang. It's not that something was hiding behind it. It's just that the concept of before loses its meaning. In fact, many physicists describe the Big Bang not as a moment in time, but as the moment when time itself became meaningful. Before that, if we can even say before, there may have been no flow of time at all, just a timeless, spaceless state outside the bounds of our physics. It's a bit like asking what your phone battery was doing before it was manufactured. It didn't exist yet. There was no function, no capacity, no timekeeping. Only after the phone is assembled, charged and powered on can it start ticking and notifying you about emails you'll probably ignore. Similarly, the universe may have been unpowered, so to speak, until the Big Bang flipped the switch. And with that flip came time, space, energy, and all the cosmic ingredients that followed. Of course, this raises a different kind of question. If time began at the Big Bang, what caused the Big Bang? Doesn't a cause require time to precede effect? You're not alone in asking that. It's one of the slipperiest concepts in all of physics. Most cause and effect relationships we know depend on time flowing forward. You toss a ball, then it flies. You pour tea, then it fills the cup. But if the universe began in a timeless state, the normal rules don't seem to apply. Some physicists speculate that the cause of the Big Bang may not be a cause in time, but a kind of boundary condition, a set of starting rules that simply are. Like a board game that springs into being with the dice already in motion. There is no first player, because the rules themselves begin the game. And here's another twist. Not all physicists even agree that time had a sharp beginning. Some models suggest that time may be more like a loop, or a bounce, contracting and expanding in cycles, with no true beginning or end. We'll visit those ideas later on, when we explore theories like the Big Bounce and loop quantum cosmology. But for now, let's stay with this strange but simple notion, that time had a beginning, that it emerged from the Big Bang, just like light, matter and motion, that before the universe, there wasn't a clock ticking in a dark room waiting for someone to press start. It's hard to wrap our heads around because our heads evolved to keep track of days and seasons, not the curvature of space-time, but in some ways, it's a liberating idea. If time had a birthday, then every second that exists, including this one, right now, is part of a grand unfolding, a story that began 13.8 billion years ago and is still being written. And perhaps most remarkably, every moment we experience is layered within that cosmic timeline. The ticking of your heartbeat, the flicker of neurons in your brain, the soft rustle of your bedsheets, all of it part of time's fabric. A fabric that, according to our best understanding, didn't always exist. So the next time someone casually asks you what happened before the Big Bang, you can smile sleepily and say, "That's like asking what's north of the North Pole." Then you can sip your tea and drift into the kind of dream only the universe itself could imagine. Because time, like a river, had a source. And for reasons we may never fully grasp, that source seems to have emerged not within time, but instead alongside it. Time had a beginning, and here we are, floating in its current, the Big Bang. It's one of those names that sticks in the mind, punchy, dramatic, and wonderfully explosive. It conjures up images of a dark, empty void suddenly lit up by a colossal boom, like the universe was born from the finale of a cosmic fireworks show. But as it turns out, the name Big Bang might be one of the most misleading titles in the history of science, and understanding why can help us see the origins of the universe and the idea of nothing before in a very different light. Let's start with a little historical trivia, because it's oddly fitting. The term Big Bang was actually coined as a joke. Back in the 1940s, a brilliant but sceptical British astronomer named Fred Hoyle used the phrase during a BBC radio broadcast. Hoyle didn't believe in the idea of a universe with a beginning. He was a champion of the rival theory at the time, the steady-state model, which suggested that the universe had always existed and was constantly generating new matter as it expanded. So when Hoyle sarcastically referred to the competing idea as the Big Bang, he meant it as a jab, a flippant nickname for what he thought was a silly, unscientific concept. The name stuck. The theory did too. Ironically, the evidence piled up in favour of the Big Bang model, and poor Fred Hoyle became eternally linked to a theory he didn't believe in, all because of a throwaway line on the radio. But let's be clear, despite the name, there was no bang. At least, not in the way we usually think of one. An explosion, in the everyday sense, happens in space. A firework goes off in the sky, sending sparks outward through the air. A volcano erupts, hurling ash and lava across the land. These are loud, violent events that happen at a specific location, with debris flying outward into a larger background. But the Big Bang was not like that. The Big Bang wasn't an explosion in space, it was an expansion of space. That difference might seem subtle, but it's everything. Imagine blowing up a balloon. You take a red marker and draw little dots all over its surface. These dots represent galaxies. As you inflate the balloon, you'll notice that the dots move away from each other, not because they're crawling across the rubber. They're fixed in place, but because the surface itself is stretching. Every bit of balloon is getting bigger, and that's carrying the dots apart. That's what the universe is doing. Galaxies aren't flying apart through some vast emptiness. Space itself is expanding. The distances between galaxies grow because the fabric of the cosmos is stretching. The balloon gets bigger, so everything on it gets farther apart, and here's the key part. The balloon doesn't have a center. Every point is moving away from every other point. There's no central explosion site. If you're standing on any one of those dots, it looks like you're at the center, with everything else rushing away. But that's just an illusion caused by uniform expansion. Our universe works in the same way. No matter where you are, you'll see galaxies receding in all directions. It gives the impression that you're at the center of the bang, but so does every other galaxy. There is no center, there is no edge, just a boundless, stretching space-time. Now let's gently rewind the balloon. If we shrink it back in time, the dots get closer together. The surface contracts. The balloon tightens down until, at some finite point in the past, it reaches a state of extreme density and temperature. A tiny, hot, uniform thing. That's our starting point. But remember, in this analogy, the balloon's surface is space itself. So when we rewind to that tightly packed state, we're not zooming in on an object in space. We're zooming in on the very fabric of space and time becoming smaller, denser, hotter, and eventually reaching a state where our current physics breaks down. In other words, the Big Bang wasn't something that happened inside the universe. It's the moment the universe, and with it, space and time, came into being. Which brings us back to the idea of nothing. Because if the Big Bang wasn't an explosion in pre-existing space, then there wasn't a waiting emptiness for it to happen in. There wasn't a cold, dark stage sitting patiently for a universe to show up and start the show. There was no container, no backdrop, no space at all. This changes everything about how we think of beginnings. In our daily lives, we expect everything to unfold in time, within a space. But the Big Bang suggests that time and space are part of the thing that began. Asking what came before it, or where it happened, may be like asking what's outside of the canvas in a painting that is the canvas. If space is expanding, then going back in time means space is shrinking. And if time itself is part of that story, then there may not have been a before in the way we usually think of it. Not because we're missing information, but because the very concept might not apply. To go back to our balloon, imagine trying to peel off the rubber and ask what's underneath the surface, but the balloon doesn't exist in three-dimensional space in this analogy. The surface is all there is. Asking what's underneath is a category error. This is why physicists tread carefully when talking about what preceded the Big Bang. Some propose that the question is meaningless, like asking what's north of the North Pole. Others think it points to a deeper mystery, that our current models are incomplete, and some new theory of quantum gravity might give us a window into a before we can't yet describe. But one thing's for sure, calling it a bang sets up the wrong mental picture. There was no shrapnel, no debris, no sonic boom echoing through a void. There was no there. What we got was the unfolding of everything, an expansion of space-time itself, from an origin point we don't fully understand. It was quiet, it was smooth, it was mathematically precise, and yet it created everything, from the stars in the sky to the atoms in your fingertips, galaxies, photons, black holes, Beethoven, banana bread. All of it has roots in that unfathomable moment when space took its first breath. So the next time someone talks about the Big Bang as if it were a loud cosmic detonation, feel free to smile knowingly and gently suggest that it might have been more of a big stretch. A calm, expansive beginning that left behind not a crater but a universe. And in that stretching silence, we find not just a new way of seeing the cosmos, but a deeper understanding of what it means for nothing to become everything. Picture the quietest place you can imagine. Maybe a dark, empty room with thick walls and no windows, no ticking clocks, no rustling wind, not even the hum of electricity. A pure, perfect silence. Now zoom out, way out, until that room becomes a patch of outer space, light years from the nearest star. No dust, no radiation, no planets or particles. You'd be forgiven for thinking you've arrived at true nothingness. But in the quantum world, even that kind of stillness is a noisy place. Tonight we're going to take a slow, curious dive into one of the strangest ideas in all of physics. The idea that empty space isn't actually empty. That even in the absence of all matter and light, the vacuum itself is brimming with invisible activity. A restless sea of possibility known as quantum fluctuations. To understand this idea, we need to visit a concept that underpins much of modern physics, quantum field theory, or QFT for short. It might sound intimidating, but we'll take it gently, step by step. In classical physics, the kind you might remember from school, the world is made of particles, tiny little billiard balls that move around in space, collide, bounce, and occasionally break into pieces. Light, for example, was once thought of as a wave, while matter was seen as particles. But quantum theory showed us that reality is far more complicated and far more elegant. Quantum field theory tells us that everything, every particle, every force, is a ripple in a field. Imagine the universe as a vast ocean, but not of water. Instead, this ocean is made up of fields, invisible layers of energy that stretch across all of space. There's a field for electrons, a field for quarks, a field for photons, even a field for the Higgs boson. These fields aren't confined to specific locations, they exist everywhere, all the time. Now here's the magical part. When a field vibrates in just the right way, it produces what we see as a particle. An electron is just a ripple in the electron field. A photon, a ripple in the electromagnetic field. It's like throwing a stone into a pond and watching the waves spread out. Only in this case, the ripple is the stone. But even when the pond seems perfectly still, no ripples, no wind, there's still energy. At the quantum level, fields are never truly at rest. They wiggle spontaneously due to the strange rules of uncertainty that govern the quantum world. This is where quantum fluctuations come in. According to the Heisenberg uncertainty principle, there's a limit to how precisely we can know both the energy and the timing of events. This means that even in a vacuum, where there are no particles and no radiation, energy can temporarily spike. For the briefest moments, particles can flicker into existence and then disappear again. These are called virtual particles, and while they're not directly observable in the way normal particles are, their effects can be measured. It's a bit like borrowing a cup of sugar from your neighbour and returning it so fast they don't even notice you were there. Except you're a pair of subatomic particles, and your neighbour is the universe. So when we say the vacuum isn't empty, we don't mean it's secretly full of stuff. We mean that even in its lowest energy state, space is still humming with jittery temporary excitations. These fluctuations are incredibly brief and small, but they are real enough to have measurable consequences. For instance, quantum fluctuations can shift the energy levels of electrons in atoms, a phenomenon known as the Lamb shift. They can cause forces to emerge between uncharged metal plates placed very close together in what's known as the Casimir effect, and they may even be responsible for some of the randomness that underlies radioactive decay. But here's where things get really fascinating and relevant to our larger question. Could this fluctuating, jittery vacuum be the true origin of our universe? Some physicists think it might be. Let's drift into the idea slowly. If space can never be truly empty, and if quantum fluctuations are always bubbling beneath the surface, then maybe, just maybe, a fluctuation of the right kind could cause something big to happen. Something like the birth of a universe. One proposal, suggested by physicist Alexander Vilenkin, is that the universe could have tunneled into existence from nothing. Not nothing in the philosophical sense, but a kind of quantum nothing, a state with no classical space or time, but with the potential to fluctuate due to quantum uncertainty. In this view, the universe wasn't caused by anything in the traditional sense. It didn't explode out of a pre-existing space or emerge from a deity's command. Instead, it could have spontaneously appeared, a quantum fluctuation on a cosmic scale, allowed by the rules of quantum mechanics. To be clear, this isn't magic. It's not a loophole. In the quantum world, spontaneous events with non-zero probability can and do happen. It's just that most of them are tiny and fleeting. But if the conditions are right, if the vacuum has enough energy, for example, a fluctuation could trigger inflation, the rapid expansion that set the stage for the Big Bang as we know it. In this sense, the universe may have emerged from a vacuum state, not an absolute nothing, but a seething dynamic field of potential, the kind of nothing that's actually quite something. Now some of you might be thinking, wait, doesn't this still leave us with something? Where did the quantum fields come from in the first place? And that's a fair question. This approach may push the mystery back a level, but it doesn't erase it. If quantum fields are eternal, then we're no longer asking where the universe came from, but why these fields exist at all. If they're not eternal, then we're back to wondering what gave rise to them. But the beauty of this idea, this quantum vacuum, is that it shows us a possible bridge between nothing and something. It blurs the boundary. It hints that what we used to think of as nothing, a silent void, may be the very stage on which existence performs its quietest, strangest magic. And it makes sense in a way that the universe would be born not from a bang, but from a ripple, a flutter in the stillness, a whisper in the dark. So as you lie there, letting your thoughts drift like particles in a warm breeze, remember that even the quietest, emptiest places are not truly empty. Not at the quantum level. They vibrate. They shimmer, they dream. And if our universe did emerge from one of those dreams, if this vast cosmos was born from a brief, improbable flicker, then perhaps nothingness isn't the end of thought, but the beginning. The vacuum isn't empty, it's just full of potential. Let's imagine, just for a moment, the quietest silence possible. A silence not just without sound, but without time. Not just without motion, but without space. No stars, no atoms, no energy, no past, no future, not even a black void, just the absence of everything, and then a universe. This might sound like the setup for a bedtime fairy tale. Once upon a time, there was no time. But in the curious world of theoretical physics, it's more than a bedtime story. It's a serious attempt to understand how everything could have emerged from what we once called nothing. Tonight we're going to float gently into one of the boldest ideas in modern cosmology, the notion that the universe could have quantum tunneled into existence. A model proposed by physicist Alexander Vilenkin and others, where reality itself flickered into being not from a divine command or a fiery explosion, but from a quiet quantum possibility. Now before we tiptoe into tunneling, let's revisit something we learned in the last chapter. The vacuum is never truly empty. Even the calmest space bubbles with quantum fluctuations, little borrowings of energy that vanish as quickly as they appear. This is because of the strange logic of the quantum world, where things that are forbidden in classical physics can still happen as long as they don't last too long. And this idea that nature has some flexibility, a kind of quantum wiggle room, brings us to quantum tunneling. In classical physics, if you throw a ball at a wall and it doesn't have enough energy to get over the top, it will just bounce back. That's it. Game over. But in quantum physics, there's a chance, a small but real one, that the ball could simply appear on the other side of the wall. Not because it jumped over or tunneled through in the usual sense, but because particles aren't like tiny marbles. They're like waves, fuzzy, probabilistic, slightly mischievous waves. And sometimes those waves allow things to appear where they shouldn't be allowed, according to our everyday expectations. This phenomenon, known as quantum tunneling, is not just theory. It's been observed in countless experiments. It's how nuclear fusion happens in stars. It's how some particles decay. And it might just be how the universe was born. So how does that work? Let's ease into Alexander Vilenkin's idea, one of the most quietly radical ideas in all of cosmology. In the early 1980s, Vilenkin proposed that the universe could have tunneled into existence from a state with no classical space, no time and no matter, in other words, from nothing. But this wasn't an ordinary nothing. It wasn't empty space. It wasn't a vacuum waiting to be filled. It was the absence of all physical structure, yet somehow still governed by the rules of quantum physics. This sounds strange, and it is. But remember, quantum physics allows for possibilities that defy classical intuition. In Vilenkin's model, the universe didn't need a cause in the traditional sense. There was no ticking clock before it, no spatial coordinates to mark its arrival. Instead, it was like a particle appearing on the other side of an impossibly high wall, not because it climbed over, but because the laws of quantum mechanics gave it a tiny but non-zero chance to exist there. This is sometimes called quantum cosmogenesis, the birth of a cosmos through quantum means, and it comes with a remarkable feature. The probability of tunneling is related to the energy of the resulting universe. That is, smaller, simpler universes are more likely to tunnel into existence than larger or more complicated ones. Now, if you're wondering, wait, how can quantum laws exist in a place with no space or time? You're not alone. It's a delicate philosophical and scientific question. Some physicists argue that quantum laws are so fundamental they don't need a pre-existing universe to operate. They're not like traffic rules written on signs. They're more like the blueprint of possibility itself. You can think of it like this. Even if there is no game board yet, the rules of chess still exist conceptually. And once the board appears, those rules dictate how pieces can move. Similarly, the pre-universe nothing in Vilenkin's model doesn't have a game board, no space-time, no geometry. But it may still be shaped by quantum rules that determine what can happen and how likely it is to happen. And according to this idea, what can happen is astonishing. An entire universe, complete with its own space, time, energy, and physical laws, can tunnel into being, and we might be living in it. So where does this leave us in our journey to understand nothing? Well, it shifts the question a bit. In Vilenkin's model, there may be no before the universe in the traditional sense, but there is a mathematical space of possibility, described by quantum laws. The nothingness isn't an empty box. It's more like a potential, a kind of seedbed of realities that could bloom, given the right moment. Or perhaps, more accurately, given the right absence of moment, since time itself doesn't yet exist in this state. This idea, the universe as a spontaneous probabilistic event, might feel strange, or even a little unsatisfying. We're used to thinking of causes. Things happen because of something else. But in the quantum world, some events don't need causes in the usual sense. They're allowed to happen by the rules of probability, not by the rules of determinism. And what's especially lovely about Vilenkin's model is that it doesn't require any exotic ingredients, no mysterious pre-existing space, no divine spark, just quantum mechanics doing what it always does, allowing unlikely things to happen, given enough time, or, in this case, giving birth to time itself. Of course, this is still speculative. No one has a telescope powerful enough to peer before the Big Bang, or into the quantum fuzz that may have preceded it. These are ideas grounded in mathematics and theory, not direct observation. But they offer a tantalizing glimpse at how the universe might have emerged not in a bang, but in a whisper of possibility becoming reality. And here's a little bonus twist. Because quantum mechanics is symmetric in time, there are models where the universe doesn't just tunnel forward into existence. It might tunnel symmetrically, with two time directions emerging from the same starting point. That is, there could be a mirror universe expanding in the opposite direction in time from ours. Don't worry, You won't meet your backward self at the grocery store. But it's another example of how strange, elegant and mysterious the quantum origin of the universe might be. So, could quantum tunneling from nothing be the answer to how everything began? Possibly. It's one of the best guesses we have, and it's a gentle, profound idea that the entire cosmos may have started as a tiny chance event, born from a rulebook that doesn't need a referee or even a field to play on. It's humbling, it's mind-bending, and it's strangely soothing. From nothing, or almost nothing, came everything. Not with a bang, but with a quantum shrug. Let's take a quiet pause, a deep breath in the darkness, and go back again. Not just to the beginning of the universe as we know it, but just before that, to a moment so brief and mysterious that it makes the blink of an eye look like an eternity. We're entering the era of cosmic inflation, a silent boom that may have laid the groundwork for the Big Bang. It's one of the most astonishing concepts in modern cosmology, and it helps answer some puzzling questions about the universe's shape, temperature and structure. But it also opens up some new ones, including what made the universe inflate in the first place, and what was there before that? To explore this, let's start with a curious observation, one that puzzled cosmologists for decades. When we look out into the night sky with our most sensitive instruments, we see that the universe is remarkably uniform. The temperature of the cosmic microwave background, the ancient light from the early universe, is nearly the same in every direction. We're talking about differences of less than 1 part in 100,000. That's an astonishing level of smoothness. But here's the riddle. Regions of space that are currently so far apart that they could never have interacted, even at the speed of light, somehow ended up with nearly identical properties. It's like baking 2 loaves of bread on opposite sides of the solar system and finding out they rose at exactly the same rate, with the same number of air bubbles and the same golden crust. How did they know to behave the same way? This is called the horizon problem, and it's one of several issues that the original Big Bang model couldn't explain on its own. There's also the flatness problem, the observation that the universe appears to be geometrically flat, meaning parallel lines stay parallel over vast distances. For this to be the case, the early universe would have needed to be balanced with extraordinary precision between expansion and gravity. Even the tiniest deviation in density would have led to a very different cosmos, either rapidly collapsing back in on itself or expanding too quickly for galaxies to form. And finally, there's the monopole problem, not the board game but the prediction from early physics theories that heavy magnetic monopoles should have been produced in abundance during the high-energy early universe, yet we've never found a single one. These problems seemed like clues, hints that something important was missing from our understanding of the universe's earliest moments. Enter inflation. In the early 1980s, a physicist named Alan Guth proposed a radical idea. What if, just after the birth of the universe, perhaps even at the very moment of its emergence, space underwent a brief period of exponential expansion, not just growing steadily, but doubling in size again and again, faster than the speed of light for a tiny fraction of a second. This is the theory of cosmic inflation, and it changed everything. According to inflation, the universe expanded by an incredible factor, perhaps by 100 trillion times, in less than a trillionth of a second. That's not just fast. That's almost unimaginably fast. But because it happened so early and ended so quickly, it didn't break any physical laws. In fact, Einstein's theory of relativity allows space itself to expand faster than light. It's only objects within space that are bound by that speed limit. So what does inflation do for us? Well, it solves the horizon problem neatly. If all the matter and energy in the universe were originally packed into a tiny region, so small that it could come into thermal equilibrium, then inflation would have taken that tiny uniform patch and blown it up to cosmic size. That's why we see such smoothness across vast regions of space today. They were once close enough to communicate. Inflation also flattened space, like pulling on the corners of a crumpled sheet. The more you stretch it, the flatter it appears. Just as a balloon, when inflated enough starts to look like a flat surface to an ant walking on it, the universe becomes increasingly flat as it inflates, so the flatness problem is solved too. And what about those pesky magnetic monopoles? Well, if they were produced before inflation, they would have been diluted to near nothingness during the rapid expansion, spread so thin that they'd be almost impossible to find. Problem solved, once again. Inflation, then, acts like a kind of cosmic prequel. It happens just before the hot, dense universe we associate with the Big Bang. You might even think of the traditional Big Bang as the after-party, the moment when inflation ends and all the energy stored in the inflating field is released in a burst of heat and light. This is called reheating, and it's the point when the universe becomes filled with particles and radiation, setting the stage for stars, galaxies, and everything else. So what sparked this period of rapid expansion? The short answer is, we're not entirely sure, but we have some compelling ideas. Inflation is thought to have been driven by a kind of field, similar in concept to the fields we discussed earlier in quantum theory. This hypothetical field is called the inflaton field, and like other fields in physics, it has an energy associated with it. Imagine the inflaton field as a ball sitting on a hill. While it rests near the top, its energy remains nearly constant, enough to drive the exponential expansion of space. But eventually, the ball rolls down the hill. As it does, inflation ends, and the stored energy of the field is converted into particles and radiation. The universe becomes hot. Time begins to tick in the way we understand, and what we usually call the Big Bang gets underway. It's a beautiful idea, one that turns a chaotic birth into a graceful unfolding. But as always, it raises more questions. For example, what existed before inflation? Was there a pre-inflationary state, a vacuum, a quantum fluctuation? Was inflation itself eternal, spawning countless bubble universes in an endless cosmic froth? Some models suggest exactly that, a process called eternal inflation, where inflation never really ends but continues in other regions, creating an infinite multiverse of pocket universes. Each bubble could have its own physical constants, its own dimensions, even its own concept of time. As just happens to be one that's slowed down enough to allow stars, planets, and sleepy scientists to emerge. And what about the inflaton field itself? Where did it come from? Was it always there? Did it emerge from a deeper set of laws? Or is it a temporary feature, like a ripple in a deeper ocean of reality? We don't know yet, but we're looking. Observations of the cosmic microwave background, the faint glow from the early universe, are helping us search for clues. Tiny fluctuations in that glow, which inflation predicts, have already been seen. They're like fingerprints left behind by the earliest moments of cosmic expansion. And maybe, just maybe, we'll find more evidence that inflation happened, or even hints about what came before. For now, cosmic inflation remains one of the most elegant, powerful, and mind-expanding ideas in science. A moment of near-infinite speed and silence, in which the universe didn't explode into being, but inflated into potential. Not a bang, not a flash, but a breath, deep, fast, and utterly transformative. A silent boom that gave us the space to exist. Imagine for a moment that the universe, our entire vast and expanding cosmos, with its billions of galaxies and glittering stars, is just one tiny bubble in an endless cosmic foam. One pocket of space among countless others, each with its own laws, histories, and possibilities. It's a humbling, almost dizzying idea. But according to a theory known as eternal inflation, this may be exactly what reality looks like on the grandest of scales. Tonight, we're going to float calmly through this vast and mysterious idea, a universe of universes, a multiverse born not from a singular explosion, but from a quiet, endless process of cosmic bubbling. A process that, if true, would mean that the idea of nothing may never have existed at all. To begin, let's return briefly to the theory of cosmic inflation, which we visited in the last chapter. Inflation proposes that the early universe underwent an incredibly rapid expansion, driven by the energy of a special field, the inflaton. This expansion smoothed out space, solved several cosmological puzzles, and set the stage for the hot Big Bang that followed. In the simplest versions of the theory, inflation is like turning on a fire hose. It blasts out a universe-sized patch of space, then turns off, and the universe evolves from there. But in the more nuanced, and frankly more intriguing versions of the theory, inflation doesn't stop everywhere. In fact, it can't. Because quantum fields are not perfectly smooth or predictable, there are tiny fluctuations in the inflaton field from place to place. In some regions, the field might drop in energy and inflation ends. That's where a universe like ours begins. But in other regions, the field might remain high and inflation continues. Those regions expand faster and faster, outpacing the regions where inflation ended. And while universes like ours stop inflating and cool into stars and galaxies, the space between them keeps growing. This leads to a self-replicating runaway process, eternal inflation. Think of it like boiling water in a pot. As it heats, little bubbles form and rise to the surface. But imagine that instead of the bubbles popping and disappearing, they became their own separate worlds. Now imagine that the boiling never stops. More and more bubbles form endlessly, each one expanding and evolving in its own way. That's the multiverse, as imagined by eternal inflation. Each bubble in this cosmic stew represents a universe. Some might be similar to ours. Others might have different physical laws, different particles, different forces, perhaps even different numbers of dimensions. In one bubble, gravity might be weaker. In another, stars might never form. In yet another, space might curve back in on itself like a sphere. The variety could be endless. And here's the truly staggering part. This bubbling isn't just vast, it's eternal. Because in the regions where inflation doesn't stop, space keeps expanding exponentially. The faster it expands, the more room it creates for new bubbles to form. These bubbles are isolated from each other, separated by ever-growing expanses of inflating space. They can't interact. They might never even know about one another. But together they form what's sometimes called the inflationary multiverse, an infinite landscape of universes, born not from nothing, but from a process that never stops. So what does this mean for the idea of nothing? Well, it may suggest that nothing, true, absolute, total nothing, never existed. There was never a blank slate, a moment of perfect stillness before something emerged. Instead, there's always been something happening somewhere, a bubbling, stretching, inflating cosmos branching out forever. In this picture, our universe didn't arise from a singular beginning. It was just one of countless nucleation events, where a region of space exited inflation and began evolving in the way we're familiar with. That means the Big Bang as we know it wasn't the beginning, just our beginning. Now this might sound like science fiction, or at the very least wildly speculative, and to some extent it is speculative. We don't have direct evidence of other bubbles. We can't peer into other universes to confirm their existence. But eternal inflation isn't just a fantasy someone scribbled onto a whiteboard. It's a natural mathematical consequence of certain inflation models that fit very well with what we do observe, especially in the cosmic microwave background. It also ties in with other branches of theoretical physics. For example, in string theory, a framework that attempts to unify all the fundamental forces, there isn't just one solution for the shape of reality. There may be a landscape of possible configurations, each with its own unique set of laws. Eternal inflation could be the engine that explores that landscape, bubbling off new universes to try out each possibility. Some physicists even argue that this helps explain something very strange about our universe, why its physical constants seem so finely tuned for life. Gravity, electromagnetism, the masses of particles. If any of them were just slightly different, complex matter might never form. Planets might not exist. Chemistry wouldn't work. No stars, no life, no sleepy science videos. But if there are countless universes, each with slightly different properties, then it's not so surprising that at least one, ours, happens to have just the right ingredients. It's not that we're lucky, it's that we're in the one place where observers can exist to ask the question. This idea is sometimes called the anthropic principle. It doesn't mean we're special, just that our presence tells us something about the kind of bubble we happen to live in. Now, understandably, not everyone loves this idea. Some scientists find the multiverse unsatisfying because it seems hard to test. If we can never observe the other bubbles, can we really call this science? Is it philosophy wrapped in math? That's a fair criticism, and one the scientific community continues to debate. But there are efforts to find indirect clues. For example, some theories suggest that if two bubble universes ever bumped into each other, like soap bubbles in a sink, the collision might leave a mark in the cosmic microwave background. We haven't seen such a mark yet, but researchers are looking. Others explore whether quantum gravity or string theory might one day predict specific patterns that confirm the multiverse. For now, though, eternal inflation remains a beautiful, compelling and speculative extension of our best cosmological models. So where does this leave us? It leaves us with a new way of thinking about everything. Not as a singular event in a pre-existing void, but as one chapter in a never-ending story. A story that's been unfolding forever, not in time as we know it, but in the boundless potential of space itself. In this view, nothing becomes a kind of illusion. There is always something, a field, a fluctuation, a slow, eternal bubbling. It's a quiet, expansive idea that the cosmos has no beginning and no end. Just an endless generation of possibilities, branching and inflating like foam in a never-emptied kettle. And somewhere in all that infinite froth there's us. One bubble with just the right balance. One flicker of light in an endless ocean of possibility. Perhaps the question isn't why there is something rather than nothing, but rather why we're in this something. Why this bubble, with these laws, with this calm patch of sky, and this delicate moment of awareness rose from the quiet sea of the multiverse. It's the kind of thought that doesn't demand an answer, just wonder, and in that wonder the bubbling continues. Let's begin this chapter with a quiet image. Imagine the universe not as a single line that begins and stretches forward, but as a breath, a slow cyclical rhythm, expanding outward, contracting inward, and expanding again. Inhale, exhale, over and over. In this calm and curious rhythm lies the heart of a theory that challenges one of our most cherished assumptions about the universe, that it began from nothing. This idea, gently provocative and deeply elegant, is known as the Big Bounce, a model where the universe didn't explode out of a singularity, but rebounded from a previous state. A cosmic do-over, a contraction followed by expansion. And at its core is a field of study called loop quantum cosmology. Now let's ease into the concept. In the standard Big Bang model, the universe begins from an initial singularity, a point of infinite density, infinite temperature, and zero volume. It's the moment when all the equations break down. According to classical general relativity, as we rewind time, the universe gets smaller and smaller, denser and denser, until, crunch, we hit that singularity. A place where space and time cease to be well defined. But physicists don't like infinities. They're usually a sign that something has gone wrong with the math, like dividing by zero on a calculator and watching it give up. And singularities, as elegant as they sound, are mathematical monsters. They tell us that our theories are incomplete. This is where quantum gravity enters the scene, the search for a theory that unifies the smooth geometry of general relativity with the jittery unpredictability of quantum mechanics. And one of the leading candidates in that search is loop quantum gravity. Loop quantum gravity, or LQG, reimagines space and time not as continuous, flowing things, like an infinitely smooth sheet, but as woven, granular, quantized structures. At the smallest possible scales, the so-called Planck scale, space itself may be made of tiny loops, like an intricate mesh or fabric. These loops aren't made of matter or energy, but of the very structure of space. They're the threads from which the cosmic quilt is sewn. Now, when loop quantum gravity is applied to the entire universe, a discipline known as loop quantum cosmology, something remarkable happens. Instead of the universe shrinking into an infinite density singularity as we rewind time, the theory suggests that quantum effects become dominant near that extreme point. These effects generate a kind of quantum pressure that resists further collapse. It's a bit like a trampoline that stretches under weight but eventually pushes back. The result? Instead of a big bang, we get a big bounce. In this model, the universe didn't begin at a singularity. It began at a bounce point, a minimum size and maximum density where quantum geometry repelled the collapse. Before that, a contracting universe, a cosmos that had been shrinking, cooling, perhaps even forming stars and galaxies before reaching the bounce and beginning to expand again, becoming our universe. It's a beautiful reversal. Instead of time having a hard beginning, it becomes a cycle. The bounce replaces the bang. The singularity becomes a bridge. This idea has several appealing features. First, it removes the need for infinite quantities, always a welcome relief in physics. Second, it offers a possible solution to the puzzle of what happened before the Big Bang. And third, it opens the door to an even more profound possibility, that the universe has no beginning at all. In a bouncing model, there may have been many cycles, expansions followed by contractions, each one giving rise to a new phase of cosmic history, each bounce wiping the slate clean, or perhaps leaving behind faint traces, subtle fingerprints in the structure of space and time. But is there any evidence for this? That's the big question, and scientists are beginning to look. One possible clue lies in the cosmic microwave background, the afterglow of the early universe. If a bounce really happened, and if some quantum features of the previous universe survive the transition, they might leave small imprints, tiny anomalies in the temperature fluctuations, or a particular pattern in the polarization of the light. So far, observations from telescopes like Planck haven't found anything conclusive. But the search continues, and future missions may have the sensitivity needed to test these predictions. Another interesting possibility is that bouncing cosmologies could help explain the smoothness and flatness of the universe, without needing inflation. In the standard model, inflation is invoked to stretch out any irregularities. But in some bouncing models, the contraction phase could naturally smooth and flatten space, making inflation unnecessary, or at least secondary. Of course, this doesn't mean inflation is wrong. In fact, some theories propose a hybrid model, a bounce followed by inflation, a little bit of everything. The universe contracts, bounces, then inflates, and finally cools into the familiar structures we see today. A kind of cosmic choreography, with each phase playing its role. So what about the deeper philosophical implications? Well, if the Big Bounce is real, it means that something came before our universe, quite literally. Not a void, not a timeless potential, but a previous cosmos. Maybe it was similar to ours, maybe not. It might have had different physical constants, a different distribution of matter, or even a completely different arrow of time. And if the bounce happens repeatedly, it challenges our sense of cosmic uniqueness. We may be just one era in a long chain of universal epochs, each one rising, evolving, and collapsing in its own time. No first cause, no singular creation, just an eternal heartbeat. This also has implications for the idea of entropy, the tendency of systems to become more disordered over time. In a cyclic universe, entropy would build up with each cycle, making each new bounce more chaotic than the last. But some bouncing models suggest mechanisms to reset entropy, or to dilute it during contraction, allowing the cycle to continue indefinitely. Still, many questions remain. What triggers the bounce? How does quantum gravity operate at these extreme scales? Can we test the predictions? Can we ever see past the bounce? Loop quantum cosmology is still a young field, and much remains speculative. but it offers a compelling alternative to the traditional narrative, one that removes the singularity, preserves time before the Big Bang, and hints at a much richer history than we ever imagined. It also softens the mystery of nothing. In this view, there never was nothing. There was always something. A previous universe, or perhaps many, leading to the one we see today. No need to explain the emergence of everything from an absolute void. Just a continuation, a rebound, a cycle. And it's oddly comforting, isn't it? The idea that our universe is part of a longer story. That time didn't start with us. That before our beginning, there was an end. And before that end, another beginning. A quiet rhythm, a cosmic breath. Inhale, expand, exhale, contract, and again, and again. So the next time someone asks what came before the Big Bang, you can smile softly and say, maybe a bounce, and maybe, just maybe, the universe has been bouncing all along. Let's take a gentle step into a more abstract realm tonight, a place where the fabric of reality is not woven from particles and fields, but from tiny vibrating strings. A place where dimensions aren't limited to up, down, left, right, and time, but stretch far beyond our senses. It's a place where the universe, as vast as it seems, might be just one membrane floating in a much larger cosmic sea. Welcome to the strange and beautiful world of string theory, and its even stranger cousin, brain cosmology. Now, don't worry if this all sounds like science fiction at first. String theory does have that vibe. It's bold, mathematically rich, and still very much a work in progress. But it's also one of the most serious attempts physicists have made to unify the fundamental forces of nature, to understand the smallest building blocks of matter, while also describing how the universe itself came to be. Let's start softly with the basics. In traditional physics, the kind you might encounter in everyday conversations about atoms and molecules, we think of particles as tiny points, electrons, quarks, neutrinos. They're considered to be zero-dimensional dots with no size, just mass and charge. But in string theory, those particles are not points at all. They are tiny, one-dimensional strings, each one unimaginably small, about 100 billion times smaller than a proton. These strings vibrate at different frequencies, and the way they vibrate determines what kind of particle they represent. A low-frequency vibration might give you an electron. A higher one might give you a photon. It's a little like musical notes on a violin string, different tones for different patterns. This elegant framework allows for the unification of forces that were previously hard to reconcile. Gravity, for instance, plays very poorly with quantum mechanics in the traditional model, but in string theory, gravity appears naturally as a particular vibration of a string, one that corresponds to a hypothetical particle called the graviton. But to make all this math work out, string theory requires something unexpected, extra dimensions. Not just the four we're used to, length, width, height, and time, but up to 10 spatial dimensions, or even more depending on the version of the theory, plus time. Now you might be thinking, where are these extra dimensions? I don't see them when I'm brushing my teeth or looking at the sky. According to string theory, these extra dimensions are compactified, curled up so tightly that they're imperceptible to us. Imagine a garden hose from far away. It looks like a one-dimensional line, but get up close and you see it has a circular shape. The idea is that the extra dimensions are like the circular shape of the hose, present but hidden at very small scales. So, what does all this have to do with the origin of the universe? This is where things get truly fascinating, and where brain cosmology enters the picture. In some versions of string theory, particularly M theory, which is like a big umbrella theory that unifies all the others, not only do strings exist, but so do higher dimensional objects called brains, short for membranes. These can be two-dimensional surfaces, three-dimensional volumes, or even higher. Our universe, according to some models, might actually be a three-dimensional brain, a kind of membrane, floating in a higher dimensional space. Imagine a vast ocean, with sheets of paper drifting through it. Each sheet is a brain. Our universe is one of those sheets. We're stuck to it, like ants walking on a piece of paper. We can move left, right, up, down, forward in time, but we can't step off the page. Now here's where things get exciting. In brain cosmology, it's possible that there are other brains floating nearby, parallel universes if you will, and sometimes these brains can collide. One of the leading ideas in this area is called the ekpyrotic model, a word borrowed from ancient Greek meaning conflagration or fire. In this model, our universe wasn't born from a singular explosion or a random fluctuation. Instead, it was born from the collision of two brains in a higher dimensional space. When these brains crash into each other, they release an enormous amount of energy, enough to heat the universe and create the conditions we associate with the Big Bang. But unlike the traditional Big Bang model, this version doesn't start from a singularity. It starts from a geometric higher dimensional event, a kind of cosmic fender bender. And it doesn't have to happen only once. In some brain models, this collision, and the expansion that follows, is cyclical. The brains pull apart after the collision, then are drawn back together again by gravity, leading to another collision, another Big Bang, and another cycle of cosmic history. It's not a one-time beginning, but an eternal dance of dimensions. This model shares something in common with the Big Bounce idea we explored earlier, the concept that the universe goes through cycles of contraction and expansion. But in brain cosmology, the bounce isn't just a quantum rebound, it's a collision in a higher dimensional space, one that's invisible to us but essential to the choreography of cosmic creation. And what about nothing? In this framework, nothing, in the absolute no space, no time, no laws sense, may never have existed. Instead, there may always have been a higher dimensional space with brains moving through it. Our universe's beginning wasn't the emergence of everything from nothing, but the transformation of energy from one form to another, the sudden release of potential trapped between colliding sheets. Of course, all of this is speculative. As elegant as these ideas are, we don't yet have direct evidence for extra dimensions, strings, or brains. The math is intricate and beautiful, but the experimental confirmation remains elusive. Still, there are potential observational clues. For instance, collisions between brains could leave imprints in the cosmic microwave background, subtle signatures in the temperature patterns of the ancient light. Some researchers are looking for these signals, hoping to distinguish brain collisions from other early universe events. Others are exploring whether gravitational waves, ripples in space-time, might carry information from such collisions. Since gravitational waves interact very weakly with matter, they could preserve ancient information that other signals cannot. Perhaps someday we'll hear the faint echo of brains colliding, a whisper from the higher dimensions. Until then, brain cosmology remains a profound possibility, that our universe is just one piece of a much larger structure. That reality includes hidden dimensions, invisible spaces, and universes stacked like pages in a cosmic book. And maybe, just maybe, our Big Bang wasn't the beginning. Maybe it was the sound, not of a bang, but of two brains brushing past one another, like silk sheets in a darkened room. So as you drift off tonight, let your thoughts wander across dimensions. Picture the universe not as a singular moment, but as part of a graceful, unseen dance. A choreography of brains, strings, and gentle collisions in a space beyond our own. In that vast quiet, the music of creation still plays. Let's imagine, for a moment, that we are sailing gently across a calm, endless ocean. There's no land in sight, no stars above, just water stretching smoothly in every direction. You might wonder, where does it begin? Where's the edge? But as you keep drifting, you begin to realize there is no edge, no sharp cliff to fall off, just an unbroken, continuous surface curving softly beneath you. Now, replace the ocean with time itself. This is the essence of one of the most beautifully subtle ideas ever proposed about the origin of our universe, the Hawking-Hartle no-boundary proposal. Proposed in the early 1980s by physicist James Hartle and the late legendary Stephen Hawking, this model offers a radically different way of thinking about beginnings. Not with a bang, not with a bounce, but with a gentle rounding off. No singularity, no edge in time, no need to ask, what came before? To understand this, let's take a slow walk through the problem they were trying to solve. In classical cosmology, that is the picture provided by general relativity, the universe begins at a singularity, a point of infinite density and temperature, where all known laws of physics break down. It's a kind of mathematical wall. We know what happens after it, but not what happened at or before it. The theory just shrugs its shoulders and says, "Here be dragons." For many physicists, including Hawking, this was unsatisfying. Not because singularities are ugly, though they are, but because they signal that our theory has lost its predictive power. If physics can't describe the beginning, then it hasn't really explained the universe. So Hawking and Hartle asked a bold question. What if the singularity never existed? Their answer, the no-boundary proposal, is rooted in the strange world of quantum cosmology, where quantum mechanics is applied not just to particles and atoms, but to the universe as a whole. Let's begin by recalling something curious about quantum mechanics. In quantum theory, particles don't move along single, well-defined paths. Instead, they explore all possible paths, and what we observe is a kind of average over all those possibilities. This idea, known as the path integral formulation, was developed by physicist Richard Feynman, and lies at the heart of quantum field theory. Hawking and Hartley extended this idea to the entire universe. They proposed that to understand the universe's birth, we should consider all possible histories, not just the one that led to what we see today, but all the paths the universe could have taken. And when they did this, something surprising emerged. At the very earliest moments of the universe, near what we think of as the Big Bang, time may have behaved not as a ticking clock, but more like a spatial dimension. That is, instead of starting from a point, time curved gently into space, forming a smooth, finite geometry with no edge, no corner, no singularity. This is where the ocean analogy comes in. Imagine standing at the South Pole. You're at the bottom of the Earth, in a landscape of snow and silence. Now ask yourself, what's south of the South Pole? Nothing. Not because there's a wall or a cliff or a forbidden zone, but because south simply stops making sense at that point. Every direction from the South Pole is north. The surface of the Earth curves smoothly. There's no edge, no boundary, just a seamless rounding off. Hawking and Hartle suggested that the beginning of the universe might be like that. Not a singularity, not a point in time where everything suddenly starts, but a kind of South Pole of time. A place where time loses its usual meaning and blends smoothly into space. In this model, the universe is finite but unbounded, just like the surface of a sphere. It has a size but no edge, a duration but no hard starting point. This might sound abstract, and it is, but the mathematical framework behind the no-boundary proposal is surprisingly solid. It involves a concept called imaginary time, which, despite the name, is not make-believe. It's a mathematical trick used to describe quantum systems more easily. Instead of time ticking along a straight line like a train schedule, it curves into a circular Euclidean geometry. By rotating time into this imaginary dimension, Hawking and Hartley were able to model a universe that is smooth, self-contained, and singularity-free. A universe that simply is, with no sharp beginning to explain away. So what does this mean for nothing? Well, in this picture there is no before the universe, because time itself doesn't extend past that smooth origin. The question, what came before the Big Bang, becomes as meaningless as what's south of the South Pole. This doesn't mean the universe popped out of nothing like a rabbit from a hat. It means that the origin of the universe isn't a moment, but a region a rounded, boundaryless place in the geometry of space-time where our usual ideas of before and after don't apply. And perhaps most wonderfully, this model allows for the spontaneous emergence of the universe from a quantum state, without the need for a singular beginning or an external cause. It's not that the universe needs a push to get started. In the no-boundary proposal, the universe is self-contained. Its laws, its structure, and its history all emerge together, like the surface of a globe rising gently from the South Pole. Now, it's important to say that this model, like many in cosmology, is still unconfirmed. It's a proposal, a beautiful one, but not yet backed by direct observational evidence. Some physicists find it compelling. Others prefer bouncing cosmologies, or multiverse models, or the classic Big Bang with a singularity. The jury is still out. But even if the no-boundary proposal turns out not to be literally true, it's changed the way we think about the beginning. It's reminded us that edges are often illusions, that what seems like a hard boundary might be, on closer inspection, a soft curve. And there's something quietly comforting in that. The idea that the universe didn't begin with a jolt or a bang or an infinite wall, but with a gentle rounding off, a smooth start, a natural unfolding. It invites us to think of existence not as an event that had to be caused, but as a whole, timeless at its core, yet filled with time. So as you lie back tonight, perhaps picture the early universe not as a flash in the void, but as a softly curving landscape. No cliffs, no before, just the elegant bend of time giving way to space. And in that graceful geometry, the cosmos quietly begins. Let us take a gentle detour now, a quiet meander away from the sharp instruments of physics and into the soft, flickering candlelight of philosophy. For while equations and models help us understand how the universe may have begun, it is philosophy that asks the deeper question, why anything at all? What does it mean to speak of nothing? What, if anything, could it ever be? The notion of nothing has haunted human thought for millennia. It lingers behind every question we ask about beginnings, endings, and what lies between. And though it may seem like a simple concept, the absence of everything, philosophers have shown time and again that nothing is anything but simple. Our journey begins, as it often does, in ancient Greece. The earliest thinkers in the Western tradition were not afraid to wrestle with big ideas. They stood on the edges of myth and reason, looking out at a world newly stripped of its gods, and tried to understand what was left behind. And one of the earliest and most stubborn of these thinkers was Parmenides, a philosopher from the city of Elea, writing around the 5th century BCE. Parmenides is often remembered for saying something that seems at once obvious and completely baffling. Nothing cannot be. In other words, non-being, true nothingness, is impossible. According to Parmenides, we can't even think about nothing, because the very act of thinking presupposes that there's something to think about. To speak of what is not is to fall into a contradiction. For him, only being exists, eternal, unchanging, and whole. This might sound like a philosophical tongue-twister, but Parmenides was making a profound claim. He believed that change, motion, birth, and death were illusions. That reality was a single, unchanging entity, and that all appearances of difference and absence were tricks played by our limited senses. Nothing wasn't just unthinkable, it was impossible. As you might imagine, not everyone agreed. His philosophical adversary, or perhaps his cosmic counterweight, was Heraclitus, who lived around the same time. Heraclitus saw the world not as static, but as a river of constant change. You cannot step into the same river twice, he said, because everything is always in flux. Where Parmenides saw permanence, Heraclitus saw fire. Heraclitus didn't focus on nothing directly, but his vision of a world built from opposites, light and dark, life and death, fullness and emptiness, made room for absence. For him, what is cannot be understood without also knowing what is not. Fast forward a few centuries to the more practical thinkers of Athens, and we find Democritus and the atomists, who gave us the first known theory of the vacuum. To them, the universe was made of indivisible particles, atoms, moving through empty space. They needed nothing, quite literally in their theory, a void in which matter could move, combine, and create the world. This was a daring move. For the atomists, nothingness was not a contradiction. It was a background, a necessary absence, an emptiness without which nothing could ever happen. Plato, however, wasn't so sure. He distrusted the senses and the notion of a physical void. In his view, the world of appearances was a pale imitation of eternal forms, perfect, immaterial patterns. To Plato, the absence of form wasn't meaningful. The real was what was eternal. Nothingness, like shadows on the cave wall, didn't deserve much attention, but it was Aristotle, Plato's student, who really grappled with the concept. He rejected the idea of a vacuum, believing that nature abhorred empty space. Every region of the cosmos, he thought, must be filled with something. Ether, air, or some kind of substance. He didn't believe in nothingness, because to him, everything that exists does so in something. Space, in his mind, had to be full. And for more than 1,000 years, this view held sway. Through the Middle Ages and the rise of scholastic philosophy, Aristotle's teaching shaped much of how Europe thought about space, time, and the void. Nothing was not real. It was an absence, yes, but not a thing in itself. Then came the scientific revolution, and with it, a slow but steady shift in our understanding. Thinkers like Galileo, Descartes, and Newton began to explore space not as a filled container, but as a geometric stage. Newton's universe especially required empty space, a backdrop of absolute space and time, where forces acted across great distances. Descartes, on the other hand, was uncomfortable with such voids. He famously said, "I think, therefore I am," grounding existence in thought itself. But for Descartes, extension, the property of taking up space, was inseparable from matter. If there was space, there had to be something in it. Still, the idea of the vacuum was gaining ground. By the time of Pascal and Torricelli, experiments showed that air had weight, and that you could in fact create vacuums. Nothingness, at least in the physical sense, seemed to be real, or at least experimentally useful. But the deeper question, what is absolute nothing, continued to haunt philosophy. Enter Martin Heidegger, a 20th century German philosopher who brought the question back to the centre. In a lecture titled, "What is Metaphysics?" Heidegger asked perhaps the most unsettling question of all. Why is there something rather than nothing? It sounds simple, but sit with it for a moment. Really sit with it. Why is there something? Why is there anything? A universe, a mind, a single heartbeat, instead of the pure stillness of non-being? Heidegger saw this as the ultimate question. He believed that we're usually so busy being, existing, doing, living, that we overlook the mystery of being itself, and behind that mystery is the void. Not a physical vacuum, but an existential absence. The possibility that nothing could have been. And yet, here we are. Heidegger's approach wasn't analytical. It was more poetic, more meditative. He urged us to stand before nothing, not to explain it away, but to experience its strangeness. The void, he said, reveals the fragility and wonder of being. It makes us aware that existence is not a given, that it could have been otherwise, that it could have been not at all. And perhaps that is the most profound insight philosophy offers us about nothing, that it is not a mere placeholder, or a background, or a technical term. It is a question, a haunting presence, a kind of silence that echoes behind every thought, every breath, every star. When science asks what caused the Big Bang, philosophy whispers, why anything at all? When physics models a vacuum, philosophy asks what it means for that vacuum to be. When cosmology builds universes from fields and equations, philosophy wonders if all of that is just a bright flicker in an eternal darkness. And while we may never answer those questions fully, perhaps that's not the point. Perhaps like the Greek sitting under olive trees or the existentialist staring into the night sky, our task is not to solve the riddle of nothing, but to dwell in it, to feel its chill, to respect its presence. Because in that space, that void, we glimpse the fragility of our own being, and the wonder that anything at all exists. A soft question murmured across millennia, "What is nothing?" And the equally soft reply, "You are something." And that perhaps is enough. Let's sit back for a moment, loosen our grip on equations, pause our philosophical wandering, and just wonder. Not about particles or fields or bounces or brains, but about the idea at the centre of all these chapters, nothing. We've tiptoed around its edges, asked what came before the universe, what lies beyond space, what happens when time begins to curl in on itself. But maybe it's time we ask something a little more fundamental. Does nothing even make sense? That might sound like a contradiction in terms. After all, nothing is supposed to be the absence of things, of sense, of structure, of being, and yet we keep trying to describe it, define it, contain it in words and theories. We ask what it is, where it came from, what happened before it. We treat it as if it's a place, a moment, a state of affairs, a something we can poke and prod. But maybe, just maybe, nothing isn't a feature of the universe. Maybe it's a feature of us. Let's approach the idea gently, beginning with something very human: language. Language is how we slice the world into manageable pieces. It lets us label things, describe patterns, share meaning. But it also creates categories, distinctions between things that may not be so neatly separated in reality. Take the word darkness. It sounds like its own thing. But what is it really? It's just the absence of light. You can't bottle it. You can't throw it across a room. You can't shine a flashlight and reveal a puddle of darkness hiding in the corner. Or think about cold. It's not a substance. It's the absence of heat. When you say your tea has gone cold, what you really mean is that it no longer contains the energetic jiggle of excited molecules. Nothing works the same way. It's a relational concept, a way of talking about the absence of something we usually expect to be there. No apples in the basket, no clouds in the sky, no noise in the room, but in each of those examples the nothing is only meaningful because of what we expected to find. It's not a thing on its own, it's a placeholder, a mental contrast. When we apply that idea to the universe, when we ask, what if there had been nothing? We're importing our human categories into a realm that may not follow the same rules. And here's where it gets even stranger. Physics, at its most fundamental level, doesn't seem to have a built-in notion of nothing. Quantum field theory, for instance, tells us that even the lowest energy state, as just the so-called vacuum, is not truly empty. It's filled with fluctuating fields, popping particles, restless uncertainty. That vacuum isn't an absence. It's a sea of potential, rich and jittery. Even space itself is not nothing. It has shape. It has geometry. It expands, curves, ripples. It can be warped by gravity, stretched by dark energy, curved by matter. It's a thing, a something. So where in nature do we find nothing? Nowhere, really. The universe abhors it. Even in the deepest, darkest corners of the cosmos, there are virtual particles dancing in and out of existence, space-time gently humming with structure. If you try to peel everything away, matter, radiation, light, motion, you're still left with the vacuum, and the vacuum is not nothing. Some scientists even suggest that true nothing, the total absence of space, time, laws and structure, may be logically incoherent, that it's not just unlikely, but impossible, because being seems to be built into the logic of reality. That's not a mystical idea, it's a mathematical one. In many physical theories, especially in quantum mechanics, nothing is not the default state. The default state is something, a minimum energy field, a fluctuating vacuum, a quantum foam. It's only when we imagine from the outside, with our human minds, our habits of contrast, that we conjure the possibility of absolute nothingness. And this may be the crux of the issue. We evolved in a world of somethings. We were shaped by a universe full of stuff, air to breathe, light to see, soil to touch, predators to avoid. Our brains are wired to look for patterns, boundaries, beginnings and endings. We think in opposites, light and dark, hot and cold, presence and absence. So it's no surprise that we imagine nothing as a possible alternative to something. But just because we can imagine it doesn't mean the universe can. In fact, some philosophers argue that nothing is a semantic illusion, a byproduct of grammar and cognition. We say things like, nothing is here, or nothing happened, and treat that nothing as a noun. But it's not really a noun. It's a negation, a way of saying that no particular thing from a given category showed up. When you walk into a room and say, there's nothing here, you don't mean there's a metaphysical void. You mean there are no people, or no furniture, or no cupcakes. The room still exists. The floor is under your feet. The air presses gently against your skin. The atoms hum with energy. Nothing, in this everyday sense, is always about something. It's always relative. So what happens when we stretch that relative concept into the realm of metaphysics, into the domain of origins and ultimate causes? Well, we start to ask questions that may have no meaning, or at least no answer within the universe's own terms. When we ask, why is there something rather than nothing, we assume that nothing is an alternative that could have existed, that it makes sense to imagine a blank, empty reality in which nothing at all happens or exists. But what if that's not a real option? What if something is the only possible configuration of existence, and nothing is a conceptual mirage? This idea, that nothing may be logically impossible, is gaining traction not just in philosophy, but in certain corners of physics. Some physicists argue that laws of mathematics and logic are not optional add-ons to the universe. They are intrinsic. They don't require space or time or energy to exist. They're the scaffolding of possibility itself. And if those laws exist, then perhaps nothing, in the absolute sense, was never on the menu. So what are we left with? We're left with a deep, quiet mystery, one that doesn't demand an answer, but a kind of surrender, a willingness to admit that nothing might be a beautiful illusion, a trick of language, a shadow cast by the brightness of being. It's not that the universe came from nothing, it's that there may have never been a nothing to come from, and maybe that's why we keep circling back to the question, not because we expect to answer it, but because it points toward the edge of our understanding. It reminds us that there are limits to what words can do, that not all questions have tidy resolutions. Some are there to stretch us, like a breath held in the quiet before sleep. So as you lie there, eyes heavy and mind adrift, consider this. Perhaps the universe didn't begin out of nothing. Perhaps it began, as it always has been, as something. And perhaps nothing is just the space our thoughts go when they try to find the end of the thread. A pause in the sentence, a soft imagined silence. Let's ease into a possibility that may feel paradoxically both immense and peaceful. The idea that something, perhaps subtle, perhaps strange, has simply always existed. Not created, not born from nothing, not sparked by a collision or conjured from a vacuum, but simply there, eternal, unshaken by time, unbothered by beginnings. It might seem like a bold claim, but in many ways this idea is one of the quietest in all of cosmology. There's no bang, no bounce, no tunnel or twist or brain crash, just a steady presence, a kind of cosmic hum that's always been humming long before atoms, stars or philosophers appeared to notice it. Tonight, we'll explore what this eternal something could be, and whether the deepest mystery of all isn't how something came from nothing, but how we ever imagined nothing could win. Let's begin with a simple but profound shift in perspective. Much of our questioning about the universe's origin is based on a human instinct that all things begin. We see things appear and disappear all the time. Fires burn out, rivers dry up, people are born and die. So we naturally assume that the universe itself must have had a beginning. But what if that's just a trick of our biology? What if existence itself doesn't require a starting point? In fact, there's nothing in the known laws of physics that strictly demands the universe began at a single moment in time. Some models allow for a beginning, a bang, a bounce, a brain collision. Others point toward an origin rooted in quantum chance, but still others open a door to something more subtle, a reality with no beginning at all. One possibility, perhaps the gentlest of them, is that the laws of physics themselves are eternal, that they've simply always been there, like the rules of a game that doesn't need a board to be real. Some physicists and philosophers suggest that even if the universe began at some point, the principles that allowed it to begin, like quantum mechanics, the conservation of energy, or the mathematics that describe probability, may not have. These laws could exist in a timeless way, not waiting in the wings, but forming the very possibility of anything existing at all. Imagine this. Instead of a grand event that brought forth the cosmos, there was always a quiet structure, a logical scaffolding, a set of mathematical truths that were never created because creation itself presupposes time, and if there's no time yet, there's no before in which to create anything. These eternal laws wouldn't be things in the usual sense. They wouldn't take up space or energy. They wouldn't need a beginning. They'd simply be, always. Like the truth of 2 + 2 = 4, not caused, not constructed, just present, waiting, or perhaps simply allowing. If that seems abstract, let's bring it into something a bit more physical. Another version of this idea is that the universe, or rather the totality of reality, has always existed in some form. Not necessarily as stars and galaxies, but as a quantum soup, a multiversal expanse, or a frothy field of potential. Something like quantum foam, the ever-bubbling, jittery background predicted by quantum gravity, may be the eternal sea from which universes like ours occasionally rise and fall. In this view, space and time as we know them are emergent, like waves on the surface of an ocean, but the ocean itself is always there. It doesn't begin or end, it just is. Always fluctuating, always simmering, always capable of giving rise to bubbles of order and meaning, little universes like ours. Think of it like this: if the quantum foam is eternal, then so is possibility. Our universe becomes one possible expression of that underlying potential. It's not the first, it won't be the last, and crucially, it wasn't born from nothing. It was born from something that never stopped being. Or consider the multiverse, an idea we've already floated through in earlier chapters. If space itself is inflating eternally, generating new universes as it goes, then there is no starting line. Just a never-ending process of creation, like a tree that keeps growing branches without ever having planted a seed. In that model, the universe didn't come from nothing. It came from something that is always coming, and this leads us to a more philosophical question. Why should we expect there to have ever been nothing at all? We often ask why there is something rather than nothing, as if nothing is the more natural state, and something requires explanation. But what if that assumption is backward? What if existence is the default, and nothingness is the peculiar idea? After all, we've never observed true nothingness. Even the quietest vacuum is full of quantum noise. Even the coldest patch of space contains particles, fluctuations, gravity, geometry. Nature, as far as we can tell, doesn't do off. The switch is always on, even if just barely humming. In this sense, something is the rule, not the exception. This turns the traditional question on its head. Instead of asking how the universe came from nothing, we might ask why nothing was ever expected in the first place. Maybe the idea of an empty, silent void was always a human projection, a mental placeholder, not a real possibility. And maybe eternal somethingness isn't just plausible. Maybe it's inevitable. That doesn't mean it's simple. Something eternal could take many forms, not just one timeless structure, but a shifting, self-renewing process. A loop of universes, a self-generating field, an ever-evolving mathematical object whose internal logic creates new patterns forever. These ideas are speculative, yes, but they all share one theme: continuity, a reality that never had a start and never needed one. In many ways, this idea is deeply calming. It relieves us from the need to find an ultimate origin, from the vertigo of a first cause. If something has always existed, then the universe isn't a riddle that needs solving. It's a mystery that unfolds, layer by layer, moment by moment, not from nothing, but from a quiet, eternal presence. You might think of it like a melody with no first note, a song that always was, waiting for listeners to notice, or like a flame that has never gone out, a candle not lit by a hand, but by the nature of light itself. So as you drift off tonight, perhaps let go of the question of beginnings. Let your thoughts settle not in the tension of how did it all start, but in the gentle peace of what if it didn't? What if there was always something? Something that doesn't need a cause, something that doesn't ask permission to exist, something that doesn't fit into our tidy stories of start and stop, because it flows beneath those stories, quiet, patient, eternal. And if that's true, then the universe may not be a miracle pulled from a magician's hat. It may be instead a poem written in an ancient tongue, one that's always been reciting itself across aeons, across possibilities, waiting in some far corner of space and time to whisper itself into your ears. And that too is something. Let's take a curious detour now, one that's less about stars and space, and more about screens and code. Tonight, we drift softly into the glowing, pixelated world of simulation theory. The idea that our universe, with all its galaxies, particles and ponderings, might actually be a kind of cosmic computation. It's a strange thought, and one that's been made all the more seductive by our increasingly digital lives. We simulate worlds every day, in games, in models, in weather forecasts and architectural blueprints. We build digital twins of reality that move, evolve and interact. So it's not a huge leap to wonder, what if someone, somewhere, did that with us? Simulation theory isn't just a quirky science fiction idea. It's been proposed seriously, if playfully, by philosophers and physicists alike. Thinkers like Nick Bostrom, Elon Musk, and even some quantum theorists have entertained the possibility that our reality might be the output of some vast computational system. If that's the case, then what happens to our big question about nothing? Let's explore gently. Imagine that our universe is running on some kind of cosmic computer, not necessarily a desktop in a teenager's bedroom, but something far more abstract. A vast informational system capable of rendering galaxies, minds, emotions, and ideas. In this model, what we perceive as space, time, matter, and energy are not fundamental. They're data structures, running on a deeper substrate of logic and rules. The laws of physics, just the underlying code. Quantum particles, probabilistic pixels, space-time, the grid on which it all runs. In this view, the universe doesn't exist in the traditional sense, it's computed. Like a video game that appears real only as long as the console is turned on, and everything we see, from the swirl of galaxies to the warmth of a sunrise, is part of an ongoing simulation, constantly updated, constantly unfolding. It's a fascinating perspective, but it also reframes our central question. If everything is part of a simulation, then what's nothing? Let's play with that. In the realm of computing, nothing is a surprisingly flexible idea. There's the literal blank space, an empty hard drive, a file with 0 bytes, a black screen with no signal. But even these aren't truly nothing. They're potential. A blank drive still has structure. It has memory cells, electrons, circuits. It's not doing anything, but it could. It's silence with the potential for song. So if the universe is a simulation, then the ultimate nothing might be no computation at all. Not just a pause program, but no hardware, no processor, no memory, no framework. A kind of informational void. But even then we hit a paradox. We're imagining a nothing that is still framed in terms of a computing system. We're treating it like a computer that hasn't been turned on yet. In that sense, we're back in familiar territory. Whether we call it quantum foam, vacuum energy, or a simulation engine, we're still presupposing something. A system that can allow things to emerge, to exist, to evolve. So what if we roll the idea back even further? What if there was never a blank drive? What if the simulation never stopped running? An eternal process, perhaps recursive, forever spawning new realities? Like an infinite game engine that procedurally generates worlds, each with its own rules, logic, and digital inhabitants, each asking their own questions about where it all came from. In this version of simulation theory, the beginning of our universe is simply the boot up of this particular instance. The server flickers to life, the data loads, and reality begins. Time starts ticking, particles coalesce, stars ignite, and eventually someone somewhere invents toast. But the system itself, the deeper architecture, may be timeless, always running, always generating new realities, always humming just beyond the reach of our senses. And that leads us to a peculiar thought. Perhaps we're not the base reality. Perhaps we're just one layer in a long chain of simulations. Maybe the beings who built our universe are themselves simulated by beings in a deeper simulation, and so on, in a long digital nesting doll of existences, each one built on rules, each one thinking it's the real one. In this scenario, nothing becomes less of a question and more of a setting, an absence of input, a zero state on the dashboard, a world that hasn't been rendered yet because no one has looked at it. And if we're being simulated efficiently, as good programmers would insist, then parts of the universe may not even be calculated until someone observes them. A kind of quantum lazy loading, where reality unfolds only as needed. This sounds uncannily like certain interpretations of quantum mechanics, where particles don't take on definite properties until they're observed. Could it be that quantum indeterminacy is just a computational shortcut? A clever bit of code that saves on processing power by not rendering what isn't currently being looked at? It's a charming idea, and not entirely without merit, but of course it's also untestable, for now. If we're in a simulation, then we're limited by its rules. We might be able to spot glitches, strange behaviours, unexpected correlations, patterns that seem artificial. But how would we prove it? Every tool we use to investigate the universe is part of the simulation. Still, researchers have proposed some speculative tests, things like detecting unnatural limits on energy, or odd grid-like patterns in high-energy cosmic rays. Others look for signs of discreteness in space, like pixels in the fabric of reality. So far there's no smoking gun. But the mere fact that we can ask the question is fascinating. Because whether or not we're simulated, simulation theory reminds us that our idea of nothing is always shaped by the context we're in. If we are part of a computation, then nothingness is not a place or a state. It's the absence of process, no clock cycles, no algorithm, no running code. But even that presupposes something deeper, a realm in which computation can happen or not happen, a meta-reality, a silent server rack in a higher plane of existence. And here we bump into philosophy once again. If we keep asking what's beneath the simulation, we eventually reach the same boundary that cosmologists reach when asking what came before the Big Bang. An edge of knowability, a wall beyond which our concepts no longer apply. Because whether you imagine the universe as a quantum field, a brain, or a server, there's always a something, a ground on which the simulation rests, an operating system for reality. So, Could we be in a simulation? Perhaps. Could it have always been running? Quite possibly. And if so, maybe nothing was never real, just a line of unused code waiting to be compiled into cosmos. And if none of this is true, if we're not simulated, if we are the base reality, then we're still left with the same mystery. Because whether this is the product of code or quarks, it still exists, and its existence still refuses to be reduced to nothing. So as you settle down tonight, close your eyes and picture the code of the cosmos. Not flashing numbers or green-tinted matrices, but something gentler, like music, like a lullaby sung by an ancient machine. And in that code, in that rhythm, in that patterned hum, perhaps there is no such thing as nothing. Only pauses between songs, only silence that waits to be filled. It's late, the room is quiet, the world is soft around the edges, and your thoughts are drifting towards sleep. You've followed this thread of nothingness through quantum fields, philosophical puzzles, theoretical universes, and gently vibrating strings. You've imagined space before time, time without space, a multiverse of bubbles, and the rounding off of beginnings into something smooth and unbordered. And yet, after all that, after all the speculations and scientific models, the theories of bounces, brains, and beginnings that may never have begun, there's still one question hovering in the dark like a quiet echo. Why does any of this matter? What does it change to wonder what came before the universe, or if there was ever truly a nothing at all? We still live our lives. We still make coffee, fold laundry, answer messages, and yawn. Whether the universe began with a bang, a bounce, a fluctuation, or a line of code, the cat still expects to be fed in the morning. So why do we keep coming back to these questions? Why do we care so much about what came before? Maybe the answer is woven into what it means to be human. Not just curious, but insatiably curious. We're a species that stares at campfires and wonders how far back we can trace the flame. We build myths and telescopes, we look up and inward, and when we run out of answers, we sit in the questions anyway. At first glance, it might seem like knowing what came before the Big Bang wouldn't make a difference to your day-to-day life. And in a strictly practical sense, that might be true. It won't help you remember where you left your keys. It won't file your taxes or fold your laundry. But that doesn't mean it's irrelevant, not even close. Because asking where the universe came from, what it's made of, whether it had a beginning, whether nothing ever truly existed, isn't really about solving a problem. It's about understanding where we stand. It's about stepping back far enough that we can see not just the picture but the frame. You, me, everyone we know. We're made of the universe, literally. Our bodies are built from atoms forged in ancient stars. Our thoughts are electric pulses shaped by the same laws that guide galaxies. When we ask what came before everything, we're really asking something much deeper. What are we in the grand story of existence? Even if the answers never arrive, the act of asking shifts our perspective. It pulls us out of the small loops we get caught in, the minor worries and the habitual routines. It reminds us that we are temporary passengers on a very old train, hurtling through something vast and beautiful and strange. And that shift in perspective can ripple through your life in quiet but powerful ways. When you remember that the universe might be infinite, that time itself might not have had a beginning, that even nothing is more complicated than it seems, you begin to see everything else a little differently too. A traffic jam might feel a little less frustrating. A quiet walk might feel a little more profound. Even the familiar rhythm of your own breath can become a kind of miracle. Because here's the thing, you didn't have to exist, and yet you do. Not just as a biological fluke, or a lucky arrangement of particles, but as a conscious being capable of wondering, capable of holding in your mind not just your own past, but the possible past of everything. That's extraordinary. And it's part of why these questions are worth asking. They're not distractions from real life. They are real life at its most wide awake. There's also something deeply comforting in zooming out this far, in recognizing that the universe has been around for billions of years and may continue for billions more. that the problems we carry, while real and weighty, are often small ripples in a much vaster sea. The deadlines, the to-do lists, the occasional existential panic about whether you're doing life right, all of it is framed by the immense backdrop of a universe that doesn't judge, doesn't rush, and doesn't demand that we solve everything. The universe asks nothing of us, and yet we ask everything of it. We ask why we're here, why anything is here, why there's something rather than nothing. And through those questions, we come into contact with our own fragility and our own wonder. It's also worth noting that these questions aren't just the territory of physicists and philosophers. They belong to all of us. You don't need a PhD to feel awe. You don't need equations to ask what existed before the beginning. All you need is a quiet moment, a curious mind, and maybe the willingness to sit with a little uncertainty. And perhaps that's the most important part. The uncertainty, the not knowing. There's a kind of peace in admitting that we might never fully understand what preceded the universe, or whether that question even makes sense. There's humility in recognizing the limits of what we can know, and in that humility, a surprising kind of freedom. Because once you let go of needing a perfect answer, you can fall in love with the question itself. You can explore, imagine, wonder, and dream. Not to arrive at a final truth, but to expand your sense of what's possible, and that expansion is a kind of growth, a kind of awakening. We often think of science and philosophy as cold or abstract, but they're not. At their best, they're acts of love, acts of reverence for the mystery of being. Every equation ever written, every thought experiment ever proposed, is a human reaching out into the dark, whispering, "Tell me more." And whether or not the universe whispers back, the reaching is meaningful. So why does it matter what came before the universe? It matters because it reminds us that we're part of a much bigger story. A story that may have no beginning and no end. A story written in galaxies and quarks and quiet questions. It matters because it shifts our gaze from the mirror to the sky. It matters because asking what is nothing helps us appreciate everything. And it matters because, at some deep level, it reminds us we're not separate from the cosmos. We are the cosmos thinking about itself. You don't need to solve the puzzle to find peace in the pieces. You don't need to know the origin of the universe to be moved by its beauty. And you don't need to find the edge of everything to appreciate the ground beneath your feet. What came before the universe, we may never know. But in asking, we find something else. A deeper connection to the world, to each other, and to the mystery of being, and that quietly, gently, and completely is enough. So here we are, at the quiet end of our long journey. We've drifted through fields of quantum foam, swum gently through multiverses, tiptoed across the rounded edge of time, and even wandered down the rabbit holes of philosophy and simulated realities. We've asked whether nothing ever truly existed. We've examined models, theories, and ancient ideas that have tried to draw a line between nothing and something, between silence and song, between absence and being. And now, gently, we arrive at a place not of resolution, but of rest. Because after everything, after bouncing universes, imaginary time, vibrating strings, and virtual hard drives, we're left with something unexpectedly soft. The possibility that not knowing might be the most honest and the most beautiful place to end up. In the beginning of this journey, we ask simple but profound questions. Did nothing ever exist? Could there have been a time before time, a space before space, a place where nothing, real, total, absolute nothing, was all there was? And we asked, what does nothing even mean? Is it a blankness we can picture, or a concept that slips through our fingers the moment we try to hold it? Now, after many chapters of slow, thoughtful exploration, the answers may still feel just out of reach. Not because we missed them, but because the questions themselves were never about arriving at a finish line. They were an invitation, a widening of perspective, a way to look at the universe and ourselves within it with a little more wonder. Maybe nothingness never existed. Maybe the universe has always been. Maybe reality has no edge, no first moment, no switch that flipped. Maybe the laws of physics, or something even more subtle, have simply always been at work, humming quietly through infinite time. Or maybe, just maybe, nothing really did come before everything. Maybe there was a true void. Not the vacuum of space, not a quiet room without matter, but the deep, unimaginable absence of anything at all. And from that nothing something arose, a flicker, a ripple, a question, a bang, a breath. We might never know which is true, and strangely enough that might be the point. There's a quiet kind of courage in being able to sit with mystery, to let questions remain open, to admit that the universe, in all its magnificence, may not yield every answer. Not because it's hiding them from us, but because some answers may not fit within the language of questions. Some mysteries may be woven into the fabric of existence, not to frustrate us, but to deepen our sense of wonder. Because uncertainty, when approached gently, is not frightening, it's freeing. Think of the sky on a cloudless night. All that space, all that starlight, all that silence. The universe doesn't rush to explain itself. It simply is, and it allows us, little, thoughtful beings clinging to a speck of rock, to look up, to wonder, to ask. And asking in itself is beautiful. Even if we never find out whether nothing came before the cosmos, even if we never peer past the Big Bang or decode the source code of reality, the act of wondering shapes us. It keeps our minds open and our imaginations wide. It connects us not just to science or philosophy, but to the whole human experience, the part of us that sits quietly and simply wants to understand. The mystery of nothingness is not a flaw in the universe. It's a feature, a space left open, like a pause in a piece of music, a place for us to rest, to breathe, to marvel, and the fact that we don't know, that we can't know, does not make us small. It makes us part of something far greater than we could ever fully grasp. So wherever the universe came from, whether it tunneled out of a quantum vacuum, rebounded from a previous cosmos, or emerged from nothing at all, here we are, alive, aware, able to ask, and maybe that's enough, to be a creature capable of wondering what existed before anything else. That alone is a miracle, a star becoming conscious of stars, a ripple in space-time, asking what made the water stir. So as you drift into sleep now, let the questions linger, not like burdens, but like lanterns. Let them flicker softly in the quiet corners of your mind. Let them glow not with urgency, but with peace. Because the beauty of the universe is not just in what we know, it's also in what we don't, in the vast stretches of silence that lie between every explanation, in the gentle possibility that some answers are not for solving, but for savouring. Perhaps nothingness never was. Perhaps nothingness is the mother of all things. Perhaps the line between nothing and something is not a line at all, but a dance. And either way, it's okay not to know. In fact, it's more than okay. It's what makes being alive in this strange, vast universe so quietly magnificent. Not knowing is not a weakness. It's an opening, a beginning,